Hi, good afternoon, everyone. So now we want to start the final session of this workshop. So the first speaker of this afternoon is Professor Kun Wan from Chinese University of Hong Kong, Shenzhen. And the title is an almost complete picture of the quantum hypothesis testing with composite correlated hypothesis. So please start.
Okay, thanks for the kind introduction. So this talk is about quantum hypothesis testing. So this is a very useful tool in quantum information theory. And now we generalize this setting a little bit to the composite correlated hypothesis. I will explain later what it is. So the archive paper are here. It's about these two archive paper recently. So, okay. So first of all, let me review a little bit what is hypothesis testing first. So hypothesis testing say if we have a black box, we don't know what is the working mechanism inside of this black box. So you can have two descriptions for its models. The first one we usually call it as null hypothesis at H0, or it can be another model which we call it alternative hypothesis H1. Don't know which one it is. But what we can do is that you can take samples from the black box to get some observation of the data. You can collect it, and based on this observation, you then make decisions. So whether H0 or H1 describe the black box more precisely. So this is a very foundational and rigorous framework for deciding between competing explanations for observed data, and it's a cornerstone for a lot of subjects, statistics, information theory, and machine learning, etc. So I can here give you a simple example what it is. So imagine that we're in COVID-19, right? So we have a person. We don't know whether this person is healthy or sick. So we have two descriptions for this person. But what we can do is that we can take samples from this person and get some statistic data with these samples. And based on these statistics, we can decide whether the person is healthy or sick, depending on the data that shows whether it's negative or positive. Okay, so the primary object for hypothesis testing is to identify what is the best model that describes the black box, but we need to minimize the probability of errors. Because when you do samples and make observations and do decisions, sometimes your decision is wrong. Because in the COVID-19, if healthy people, you get a test, but the test shows that it's positive, means that the person here is sick. So you make an error, right? Sometimes we call this as a type 1 error. And on the other hand, if the person is sick, but the test shows that it's a negative result, means the person is healthy, you also make a mistake. So in this scenario, you have at least type 1 and type 2 errors. So the object is that we need to identify the best model, but we need to minimize the error probabilities. So this is hypothesis testing. So this model has been leviated to the quantum case. We call it quantum hypothesis testing. So the model is very simple here, very similar to the one that we introduced before. So now you have a quantum stage in gray. You don't know if the quantum state is described by rho or it is described by sigma. You don't know what it is. It's a quantum status. But what you can do is that you can take samples from this quantum stage. You design a binary measurement, POVM measurement, and based on the measurement outcomes, either is 0 or 1, you decide the state is rho or sigma. For example, if the outcome is 0, you can decide the data is rho. If the outcome is 1, then you can decide the data is sigma. Okay, so of course, in this situation, you also make two kind of mistakes. The first one is type 1 error. So the original data is rho, but the random measurement outcome tells you that it is sigma. Okay, so this is called type 1 error, and we can calculate the error probability by taking the inner product of rho and the measurement operators. And also, you have type 2 error. So the truth is is that the data is sigma, but the outcome tells you that let you make the decision that the data is rho. So this is called type 2 error, and error probability is simply the overlap between sigma and n. Okay, so this is the quantum hypothesis testing. Of course, you can take multiple samples from the black box and then perform a joint measurement on all the collected quantum states that you have. Okay, so and still make the decision whether it's rho or sigma. So here, the quantum state you have is rho tensor n and sigma tensor n, and you can calculate type 1 and type 2 error probability as well. So usually, the type 1 and type 2 error, there's a trade-off, non-trivial trade-off between them. So we ideally want to make sure that both of the errors are very small. This is the ideal case, right? Type 1 error small, type 2 error small. But this is not the case in general. So usually, if we want to make type 1 error large, then the type 2 error can be decreased. So which means that the minus log of type 2 error will be increasing. So if we have a coordinate with the x-axis as minus log type 2 error and the vertical axis as type 2 error, then we can draw a diagram. So you'll see that usually it will be monotone increasing in this coordinate. Okay, alpha n goes up and minus log beta n also goes up. So if you draw a diagram for specific n in practice, so sometimes the curve will look like this. Okay, if you draw another curve for larger n, for example, n equals to 100, you have a different curve, right? And then you can slightly increase the n that you draw. In this case, is 1000. You have another different curve, and you can draw plenty of curves like this by increasing the block length n. You'll see the curve will eventually end up with a limit. Okay, so in this scenario, we have different operational regimes that can be studied. Okay, the first regime is called Stein's regime. So we fix the type 1 error alpha n, and we observe what is the behavior of the type 2 error, whether it converges and where it converges to. Okay, so this means that in this coordinate, we draw a horizontal axis, a horizontal line, reference line in green. Okay, we fix the type 2 error we observe, and we consider in this direction, for example. So the first point we get intersection of the curve with this reference point is this point, this one, right? So and then you have another point on the curve when you increase n a little bit larger, and when n increases the intersection point, you will see that they will eventually end up with a limit somewhere like this. And you can also do the same thing on the left-hand side. You have another alpha n slightly smaller, and you observe what is the behavior of the type 2 error when you increase the number of n while fixing the type 1 error probability. And usually you'll see that no matter what kind of alpha n you fixed, the type 2 error always exponentially decays, and it decays at a particular rate given by this Stein's exponent. So this is a constant value. You'll see that all the dots eventually converge into this value. Okay, this is called Stein's regime. So you mathematically you fix the type 1 error probability within a threshold epsilon, and you optimize the type 2 error probability, and you observe the behavior. And this ultimate limits we later know that it is given by essentially given by the relative entropy between the quantum states rho and sigma. Okay, so this is also so-called quantum Stein's lemma by Hirai and Pez, and also Nagaoka and Ogawa. So with this, we can have another regime to study. So for example, if we consider the left-hand side of this figure, we can fix the exponential decay rate of the type 2 error, which means we draw a vertical line in red like this, and we also observe what is the behavior of type 1 error if we increase n to infinity. Okay, so you'll see that all of this type 1 error will essentially converge to 0, right? And then you can ask the question, how fast it converges to 0? So what is the optimal rate for that? So this is called the error exponent regime. Mathematically, it means that you have you control the type 2 error that exponentially decays no more than the rate by r. Then you optimize the type 1 error and you observe the asymptotic behavior of type 1 error. So in this case, the optimal exponent is given by the so-called quantum Hofstadter divergence between rho and sigma, something analog to the relative entropy between rho and sigma, but in this case, it's slightly different. So these are given by sequence contributions by Ogawa, Hayashi, and also Aldernet et al., a sequence of papers to finally determine what is the optimal behavior in this regime. Of course, on the right-hand side, you can do the same thing, but if you draw a vertical line that is larger than the stance exponent here, on the right-hand side, you'll see that the type 1 area will converge to 1, right? If the curve goes darker, means that the block length n goes larger. So in this sense, in this case here, the dots will converge into the extreme case 1. So we can also ask the question how fast it converges to 1. So we observe the quantity that is minus log 1 minus alpha n. So alpha n goes to 1, so 1 minus alpha n goes to 0. We take a log. This will give us the exponent for the decay. So this is so-called strong converse exponent. So you control the type 2 error probability and optimize the type 1 probability and observe the asymptotic behavior. So in this case, the optimal behavior is characterized by the strong converse exponent. So we have a HR star here. The notation is very similar to Hofstadter divergence. This is also sometimes called quantum Hofstadter anti-divergence, okay, between rho and sigma, another quantity. So this is found by these two papers. Okay, so this is third regime. And of course, we can also have a symmetric scenario. So why do we have to control one and observe the behavior of the other? We can also minimize the error probability, the average error probability between type 1 and type 2 error. So in this case, these are called Chernoff regime. Okay, so if you have a prior probability pi 0 and pi 1, then you can calculate the average probability between type 1 and type 2 error probability and minimize this average probability. So you and you observe the asymptotic behavior when n goes too large. So essentially, this one will be characterized by the quantum Chernoff divergence, another divergence between rho and sigma. Okay, so this is a contribution by Aldernet and Labum and Scholar. Okay, so essentially for quantum hypothesis testing, you can play around the trade-off between type 1 and type 2 error probability, and you have a few regimes that you can study. So the summary in the existing result is here, okay, in this diagram. So all of the regimes are precisely characterized already by certain information measures between rho and sigma. And we can also list a table here. So the staying exponent is precisely characterized by quantum relative entropy, exponent by Hofstadter divergence, strong converse exponent by anti-divergence, Chernoff exponent by Chernoff divergence. Okay, so this gives us a complete understanding what happens for quantum hypothesis testing if we have the IID source. These are the existing results. And now we want to study the scenario that is beyond IID. So sometimes in the practical scenario, so the description that we have from the box is not a single quantum state, but a set of quantum states. Okay, so here this is referred to as composite hypothesis. For example, in Brandon-Polanius generalized Stans lemma setting, they're comparing rho tensor n with a set of all separable states, which is a set, and also some people also consider a case that you have the description of the null hypothesis as a set of S, and then you draw samples from this S. Then essentially the description of your samples is given by this set. And also sometimes the systems in different parties may correlate with each other. This happens very often in the quantum information theory. So we call this as correlated hypothesis. So rho n and sigma n is not necessary the IID, the tensor product structure, but a general entangled quantum state. So this this scenario has been studied by Milan and Ogawa. In some of the literatures, they consider that there's some physical system in the spin chain that are natively correlated with each other. Okay, so this motivates us to consider a more generic case, which is called composite correlated sources. So mathematically, it can be easy. So you have two sets of quantum states. Okay, not rho and sigma, but the two sets, an and bn, and you don't know which one it is. Again, you can draw samples from these two sets, and then make measurements to test the sample and make decisions based on the data that you collected, whether it's coming from an or coming from bn. So in this case, because you have limited knowledge of what happens in the set, right? So you need to minimize. We think of the worst case scenario. You need to minimize or maximize all the possible errors that you can obtain. For example, you take a rho n from the first set, you calculate the type of error first, and then you supervise all the possibility of the errors that you make. And finally, you find a measurement mn so that this mn will suppress all the possible errors in the end. This is the worst case scenario. Of course, once you have the type 1 and type 2 error probability, you can examine all of the previous scenarios to study the trade-off between type 1 and type 2 error probability and see what happens in the asymptotics. Okay, of course, once you introduce model, you have many challenges occurs. The first one is that you no longer have the IID structure because all the rho n or sigma n you sampled are essentially correlated. And also here the test, because you have limited knowledge of what happens inside the box, so the test you design has to be state agnostic, which means the test M should be independent of a specific rho or sigma in the set. So this is a challenge task. And also this will natively gives you a minimax problem. So you need to maximize over all the possible states in the black box, but you need to minimize all the over all the tests that you can construct. So these are the challenges. In terms of the stance expert regime, we have a few progress recently, and especially the first one is given by Hayashi and Yamasaki for the generalized stance lemma setting. So here, an is still given by rho tensor n, but bn can be a general set, satisfy a few assumptions. And also we have another result by me and my collaborators consider two general sets, rho an and bn. But all of these results, stance expert results, has to assume a few assumptions on the set we are working with. Okay, so because here this is a more general result than the IID case, it will naturally give us a more new applications in quantum cryptography, communication, scenario, or resource series. Okay. So in this talk, I'm going to introduce the trade-off of this type 1, type 2 error probability in the rest of the three regimes. Okay, error exponent, strong converse exponent, and turn-off exponent. So we hope that this result together with the stain exponent will give us a more comprehensive understanding of the composite correlated resource. So in particular, all the results that we introduced in this talk only requires very minimum assumptions on the set. In particular, we only require two assumptions that are frequently used in the literature. The first one is that the set is convex compact, and also they are closed or stable on the tensor product. That's the only assumption that we need. So it's a very generic general result. Okay. So let's go to the first regime that we consider is error exponent regime. So here on the left-hand side, this is the IID case, right? So we fix the type 2 error, we minimize the type 1 error. Finally, the limit of this exponent is given by the Hofstadter divergence, which is an optimization problem with respect to the path range divergence. Okay, so once we generate this result to the composite correlated hypothesis, we can also introduce the type 2 and type 1 error probability and introduce this optimal type 1 error probability by optimizing all the possible measurements. And then the question asks where this optimal type 1 error probability converge and where it converges to. So a natural guess is that it should converge to something very similar to the quantum Hofstadter divergence, right? But the challenging here is that how can we define suitably define what is the Hofstadter divergence between two sets of quantum states. So this is the Hofstadter divergence. At least we have two approaches to for doing the extension. The first one is to regarding the divergence as a black box, as a divergence. Then we extend it by simply infimum all the possible choice of the states from the set. So if you think of divergence as a distance, this will be the distance between the two sets. Right? This is a very natural extension. But the other extension is that we make explicitly the expression of the Hofstadter divergence. We extend the path divergence to the divergence between these two sets, and then we make use of the explicit expression for Hofstadter divergence after that. So this will give us a extension version 2. Then there's a native question asked, are these extensions equivalent or not? Okay, so essentially, if you write down everything more explicit, you will see that eventually the question is asking you whether the left-hand side given by the infimum min-max problem is whether it is equivalent to the right-hand side, the max-min problem. So usually min-max optimization cannot be swapped, but if you check a few assumptions, then you can apply the minimax theorem to exchange the min and max. So in this case, we can prove that the object function that we optimize is a convex function in terms of the state, and we change of the variable of alpha to another variable u, then we can argue that the object function is essentially concave in the parameter u. So this will satisfy the assumptions that is required to apply the minimax theorem. So essentially, we can prove that these two quantities are essentially indeed the same. We apply the minimax techniques, and so on the for finite n, these two extensions are the same. We can also extend it to the regularized case, infinity case. So on the left-hand side, we regularize by taking n goes to infinity. On the right-hand side, we introduce the regularization for the path range divergence first, and then use the explicit expression here. And also, we can ask the question whether these two extensions are the same or not. And essentially, write down everything explicitly. You'll see it will ask you the question whether this minimax problem can be exchanged or not. And here in this case, we have this direction of inequality. This is for minimax inequality. This is trivial and holds for every cases. Okay, so we know that the extension from the left-hand side is low smaller than the extension on the right-hand side. But proving the equality can be challenged here because both of the feasible sets is not compact sets. So we don't know how to argue the minimax equality. Okay.
So
Yes.
I think there is some counter example.
For which one?
That inequality. So of course that equality does not hold.
Oh, you have a counter example.
Already, Lami's paper point out that problem.
Which paper by Lamy?
Some paper.
Okay.
And in that case, left-hand side of IID, and that beta is some separate.
Okay, great. So we have a strict inequality. That's better, even better. Okay. So at least we have this direction of inequality. Okay, so direction means that the left-hand side is no smaller. And now you can ask a question, which one is the truth, right? That characterize the optimal performance in the asymptotic case. And we show that, okay, the left-hand side is the truth. Okay, so the optimal arrow equivalent when n goes to large, goes to infinity, the type 1 error probability will converge to the extension on the left-hand side. So this is the first main result. Okay. Okay. This of course is This is a slight view of how to prove it. For the lower bound, we make use of the ordinate inequality, which is quite straightforward. For the upper bound, we make use of a few fundamental properties. The first one is that the lower limit is always smaller than the lower limit of the subsequence of for any sequence of numbers. Then we can make use of minimax theorem to pull out the study of each of the states that we optimize over. And then by using the stability assumption for the set, we can take any feasible solutions in the supermem to construct an IID state. And because it's an IID case now, so we can apply the Hofstadter divergence for the IID scenario to get the Hofstadter divergence between two specific states. And this argument is independent of which state that you choose from the set. So you know that it's lower upper bounded by the divergence between the set, and then you regularize over n. And this is a sketch of the proof. Okay, so actually for the second regime, strong converse exponent regime, we can do everything in a similar way. Okay, so the left-hand side is still the IID scenario. So the optimal behavior of the type 1 probability will converge to 1 with this quantum Hofstadter anti-divergence. We call it anti-divergence because usually divergence satisfies data processing inequality. If you apply an operational channel on the data, the divergence becomes smaller, right? So here the anti-divergence means that when you apply a channel, the divergence goes larger. That's why it's called anti-divergence. Okay, so it is given by this optimization problem over sandwich Renyi divergence with the parameter alpha. And now we extend to the composite correlated scenario, define it in a similar way, ask the same question. And also the difficulty or the challenge is still what is the suitable quantity that governs this general task? How to define this anti-divergence between two sets of quantum state? And again, okay, you have two kinds of extensions. The first one is to use the anti-divergence as a black box because anti-divergence. So here we take the supermem over all the possibilities. On the right-hand side, you can extend it first for the sandwich divergence first and make use of this explicit expression. After that, can still ask the same question: are they equivalent and why they are equivalent? So essentially, you write down everything more explicitly. You'll see you have two layers of supermem. So this is trivial, right? So there's no minimax problem here. This supermem can be swapped freely. So the equality holds. And now we extend it to the regularized case, and you ask the same question whether they are the same. In this case, it's slightly challenging here, but we can still argue the equivalence. So the object function, you can prove that object function is increasing in n, and also after you supermise over alpha, this function is still increasing in n. So this helps us to, if you have a sequence of increasing lambdas, then you can replace the limit as a supermem. So essentially, you have two supermem to work with, so you can swap them freely. So the case is also easy here. So for strong converse excellent, if we extend in two different approach, but they come out as eventually the same thing. And also, okay, so everything is the same. So we prove that strong converse excellent in the composite setting is lower bounded by this regularized quantity. Okay, so proving the upper bound is a bit challenging now. So that's why I would say it's a almost complete picture. Okay, so this part is missing. The upper bound of achievable part for strong converse is missing now. So now we have the error excellent and strong converse excellent results, and what can this result help us? Whether it can give us more insights, right? So here we show a refinement of the Stein excellent regime here. So these are the error excellent and strong excellent results we have from the previous slides. And if we apply the same assumption that we have for the Stein's excellent setting, we will essentially have a continuity for this regularized divergence with respect to alpha. if you supermise alpha, the path divergence will converge from below to the omega k1, and infimum with alpha, it will converge essentially to the from above to the omega k divergence. Okay, so this means that for any r constant number r that is smaller than the regularized relative entropy, you can always find the alpha such that this quantity is strictly positive. Okay, and you can do the same argument for alpha is larger than the divergence. You can always find, because it's continuous function, and you show the continuity when alpha equals to 1. So if r is strictly larger than the divergence, you can argue that this exponent here is strictly larger than 0. Okay, so this will be a stronger result than the stance exponent that we have, because if r is below the divergence, which means everything is achievable, and we know the type 1 error probability will decay exponentially, at least with this non-trivial rate. And if r is larger than this threshold, we know the type 1 error will converge to 1, but also converge to 1 exponentially fast at this non-trivial rate. So this is a this refines the stance exponent regime and sets the regularized relative entropy as a sharp threshold for the trade-off. Okay, so this is one application. Of course, if you want to recover the stance setting by Baranda-Planio and have another alternative proof for the stance lemma besides the one by Hayashi and Yamasaki and also Ludovico, we need this asymptotic continuity with the corresponding assumption. But this can be challenging itself. You know, you have a counterexample? Okay.
If this is hold, so I already prove much easier.
Okay, great. So this means what? This means the things here are much more interesting than we thought.
Because that Ramin's paper already point out that equality does not hold in the case of separability. They already give some counter example.
For this asymptotic continuity. Okay.
No. So they prove that kind of counter example. So
okay, great.
Does not hold.
That's great. So I guess so the stance setting here is can be much more complicated than we expected. Good. Thank you for the comments. Okay. So at least for the assumption that we apply, the polar assumption, everything works here. Okay. Good. So of course, the last setting that we consider is Chernoff exponent. So which means we average the error probability of type 1 and type 2. And the classical, the existing result tells you that in the IID case, this is governed by the Chernoff divergence, which is essentially something like very similar to path divergence here. And you repeat the argument that we have for the previous settings. How can we define the Chernoff exponents for two sets of quantum states? Okay, first extension regarding as a divergence itself, infimum all the possibilities that you have. The other one is that you extend the divergence or the quasi-divergence inside of this expression first, and you make the explicit expression for Chernoff divergence for extension. This is extension 2, and still whether the same or not. This is also a minimax problem, but it behaves very nicely. So we know that this quasi-divergence is concave with respect to the state and convex in terms of alpha. So you can put this infimum and maximum inside of this log to apply the minimax theorem by seeing a standard one. Then you know that the minimax holds. So these two extensions are essentially the same. And also you extend it to the asymptotic case, and we're asking question whether they're the same. Write down everything more explicitly. Okay, so this is slightly more complicated than the strong converse exponent. We have the minimax problem here, but you can still argue that okay, the object function behaves nicely, is semi-continuous and monotone in N, and also you can apply another variant of minimax theorem by Masoya and Yai in the paper. So it's very important that for Chernoff divergence here, the maximum over alpha is a compact set. This is very important fact that we use. Otherwise, you cannot apply the minimax theorem. Okay. Anyway, so we proved that the minimax also holds for the regularized quantity. So they're essentially the same thing. So and we proved that the Chernoff exponent for composite hypotheses are precisely characterized by this regularized Chernoff divergence. Okay, this is the result. So it's a in this case it's a very clean result here, and we can also extend this to multiple hypotheses. You have if you assume that set are more also permutation invariant, you have a similar result. So we can extend the result by Curly to the composite hypothesis. Okay, so finally we have more interesting result here. So for the Chernoff setting, we actually know what is the optimal task here. So this minimum error probability is essentially can be written down as a trace law between the states. So we know the optimal measurement here is essentially given by the positive part of the state, which is so-called Hallström's test. But now we want to have similar thing for the composite hypothesis, right? But now in this case here, this is very non-trivial because the measurement now we want to design should be independent of a specific quantum state that we choose here. So what is the optimum task for composite hypothesis? So we give a more detailed analysis here. You write down the minimum error probability for composite hypothesis. You have this minimax optimization. So you can easily prove that because type 1 and type 2 error probability are essentially a linear function with respect to all the variables. So you can easily argue that minimax holds for this error probability for fixed lambda of n. But we have different. So this minimax inequality provides us two perspectives to look at the same thing. From the left-hand side, we need to design a quantum measurement that is independent of the specific choice. But on the right-hand side, the infimum over the measurement can be defined with respect to rho and sigma n. Because the understanding here is that you fix rho and sigma n first, and you solve the inner minimization problem, and then you optimize over all the possible choice. So this Mn in the inner optimization can be depend on the rho and sigma n that you choose. So the left-hand side is essentially a black box setting. No matter what kind of state that you choose, the test should universally works well for any possibilities that can happen. Right? Black box setting. But on the right-hand side, we can pick the hardest pair of states to discriminate, and then we design the optimal measurement based on that state. So here we can simply make use of choose the optimal state rho n star and sigma n star that has the largest has the closest trace distance, and we can find the optimal test on the right-hand side is essentially given by the high-level Hallström test. But is this test also optimal on the left-hand side? So this is a non-trivial question, right? We found a minimizer on the right-hand side, whether this minimizer is also a minimizer on the left-hand side. So here we have a, why it is non-trivial, we have a counterexample here. So if we minimize of this simple function x times y, you will see that the minimizer on the right-hand side can be anything between -1 and 1. But the minimizer on the left-hand side is unique 1. So you solving the minimizer on the right-hand side does not directly give you the minimizer on the left-hand side. This is a counterexample. So the thing here, constructing the minimizer on the left-hand side is a non-trivial task. But we prove this if we can assume that the state of this is full rank. So this essentially help us to claim that the minimizer on the right-hand side is also unique. In this case, we can say the minimizer is also a minimizer on the left-hand side. It will be the universal test that we want under these assumptions. Okay. Finally, we'll have a small application. So, for example, this maximum overlap appears very frequently in resource theory. But the first, we can connect it with Chernoff divergence. If the first one is pure state, it simply simplifies to maximum overlap. So it gives a operational meaning of this technical quantity that always happens in resource theory. And also, we know in the resource of magic, we know that the maximum overlap is not multiplicative. We have a counterexample here. So this automatically implies that the Chernoff divergence between two sets is not additive. So this justifies the regularization of this notation here. Okay, as a summary, so we give a comprehensive study of the composite hypothesis testing problem and study the error excellence, strong converse and Chernoff excellence regimes. And we hope that these results, together with the Stein excellence regime, give us a more complete picture for this set, for this generalized set. And it's very important that, okay, for all the excellent results that we have, we only require these two assumptions. It's very minimum one. It's a very general result. We say it's almost complete because there's a missing part for the strong converse excellent, right? So we don't have the achievability part. Of course, for the potential applications, so because now we have a more general technical tools for hypothesis testing. So basically, we can explore every information test that is related with hypothesis testing, like channel coding, discrimination, or anything else. So. Okay, so this end of the talk. This is the last slide. I'm hiring, so if you're interested in working with me, you can drop me an email. And thanks very much for your attention.
Okay, thank you very much. So is there any question or comment? Yeah, or Nagoya side? No comment from Nagoya side?
You haven't. No, sorry.
Oh. Firstly, so you cited several papers in the IID case, but Nagaoka, Ogawa, but first author is Ogawa. So at that time, Ogawa was a PhD student and Nagaoka was a supervisor. So you should change that order. Ogawa Naga.
Which one for Hofting?
Stein's lemma and anti-strong bombers. So this one, not Nagaoka, Ogawa. Ogawa, Nagaoka. Ogawa is a PhD student and at that time, and Nagaoka was a supervisor.
Okay. But
Not only this one, and also that Stein's lemma.
okay, so I will double check the reference. Thanks.
And also Rami's paper, Rami and some other guide paper, they consider composite hypothesis for the maybe for the first argument. So in that case, they consider so many good counter examples. So in that case, the limit of that kind of linear entropy does not work.
Okay, yeah.
In a separate case. So of course, if the state right hand side, this is the IID, if that state is maximally correlated, so in that case, quite easy. So because in that case, we have additivity for the that kind of linear divergence. But generally, linear divergence does not satisfy additivity.
Yes.
So, but the that kind of relative entropy, if the second argument, the first argument is composite in the separate case, in that case, we can relatively easily prove the additivity.
Yes.
So right hand side is different, so, but right hand side composite state. So in that case, not so easy, but right hand side is only one element, and left hand side, left argument is composite. In that case, relative entropy satisfy additivity. But if you change the alpha, so in that case, it is quite difficult to generally that kind of additivity does not hold.
Yes.
So in that case, if you take the alpha going to 0, but in that case, you cannot recover the how to say, you cannot recover relative entropy.
Yes.
So this is their counter example. So
That's nice.
they show the very interesting counter example.
Okay. So this means that we have the Stein's excellence in Brando-Planius framework, but it's very challenging to get the error explained further. Can we?
Planius version, Planius of Brando case is beta is composite. But now I mention that alpha A is composite.
Yes.
Not, I don't know, B is composite case, maybe, I don't know, additivity falls or not, maybe not, but I don't
Okay.
know.
Okay, yeah, thanks. Okay.
Is there any comment or question? So thank you very much. So then what is the next talk? So next talk is
Of Nagoya.
Nagoya side. So from it's here.
長谷川さん。
From 20. So 4 minutes. So please prepare.
Yes, please, wait a moment. Can you hear me? Can you hear me?
Yes.
Okay, thank you. Using this one, okay. What are you on? Did they prepare the? But I'm afraid where is the next speaker? He don't want to come here. Don't know where it is. So then, this is the reason why I organized this conference training. The time. So now we want to proceed the second talk. The second speaker is Atsuya Hasegawa from Nagoya. Now we want to start the second talk of afternoon session. The second speaker is Atsuya Hasegawa from Nagoya University. The title of his talk is Does there exist a quantum fingerprinting protocol without coherent measurement? So please start.
Thank you for the introduction. And thank you for the introduction. Can you hear me? Okay, so I'm going to talk about some result on the quantum fingerprinting. This joint work is based on joint work with Srijita, Francois, Harumichi, and Kishen. Okay, so my talk will be based on communication complexity and quantum fingerprinting, which has some overlap with Harumichi's talk yesterday. So let me quickly remind basic concept. So the communication complexity was introduced by Yao in 1979, and the object of the field is to identify minimum amount of communication to solve some problem in distributed setting. Okay, and this is a basic setting of communication complexity. And in my talk, and maybe Harumichi's talk, I will focus on simultaneously message passing model, SMP model, as in the slide. So in the model, there are three parties: Alice, Bob, and referee. And Alice and Bob receive inputs, and referee want to calculate some function based on messages from Alice and Bob. And the complexity of the model is sum of two messages from Alice and Bob. And the most basic function in communication complexity is the equality function. And there is one open problem in the original paper by Yao. So Yao realized if Alice and Bob are allowed to share some randomness, then the equality is very easy. So the communication complexity is constant. So without shared randomness, the complexity for the equality problem in the SMP model was non-trivial and mysterious. And in the 1990s, Ambinest first showed that there exists upper bound with order of root n bit communication. And subsequently, Newman, Segedi, and Baba and Kimmel show that the bound is tight. So the Yao's open question was an open question by Yao in 1979 was solved. And in 2001, Berman, Kriep, Watters, and DeVolk discovered that in quantum setting, there exists an efficient protocol. And the complexity is log n. Okay? And classically, the complexity is root n. So in the between classical and quantum SP model, without shared randomness, there exists an exponential separation in the communication amount. And importantly, the referee does a swap test in the protocol, fingerprinting protocol, quantum fingerprinting protocol. So this discovery can be also viewed as a application of the swap test. So this protocol is important in my talk. So let me quickly remind the protocol. So Alice and Bob generate their fingerprinting based on their inputs and send them to the referee, and the referee does some entangle measurement, the swap test and entangle measurement over two messages, Alice and Bob. So as I recall, Haramichi discussed yesterday, the construction of fingerprinting is superposition of some error correction code, linear error correction code of their inputs. Okay, and yeah, the referee does the swap test between two messages, Alice and Bob. So in the quantum fingerprinting protocol, we exploit two type of quantumness. So first is superposition, and the other is entangle measurement. Okay. So in our work, we consider setting where Alice and Bob can send quantum message, but the referee cannot do an entangle measurement, including the swap test. So in the setting, does there exist an efficient SMP protocol? And here, efficient means some like polylog and qubit communication, which exhibit an exponential advantage over classical setting. And some type of measurement, which is not entangle measurement, is so one type of such measurement is LOCC measurement, which is intensively studied in the field of quantum information theory. So in LOCC measurement, states are locally measured, and the measurement result can be shared with some classical communication. So in our work, we introduce a quantum LOCC SMP model. Okay. So referee receives quantum messages from Alice and Bob, and the referee do some LOCC measurement over two messages. And so when we start such investigation, we found that a very related model was already studied. So SMP model, where one message is classical and the other is quantum, was introduced by Gavinsky, Legev, and DeWolf in 2008. And let's call it a hybrid model. And they and subsequent work show that the equality problem is still hard in the model. So as I said, classically, the complexity for the classical SMP model, the complexity is root n, and even for the hybrid model, the complexity is the same. So no advantage, even if we can replace one classical message by quantum message. So this is a relation between our setting and the previous result. So if we are a full quantum, if we can consider full quantum model, equality problem is very easy. However, for classical model and hybrid model, the problem is hard. So our model is between full quantum model and hybrid model. And in our work, we show that we consider some restrict type of LCC measurement. First, when we consider one-way LCC measurement, then root and qubit communication is required. So there's no quantum advantage in the setting. And even we further show that even when we consider some restrict type of two-way LCC measurement, some Fourier qubit communication is required. So no exponential quantum advantage even in the setting. And as a last result, we show that exponential separation between one-way and two-way LCC model. So when someone see the first result and second result, one might consider quantum LCC maybe model is just a weak model. But our third result implies that the model can be exponentially stronger than hybrid model and full classical model, and even quantum one-way LCC. Okay, so in the remaining time, let me talk about some sketch of our proofs. So in quantum one-way LCC SMP model, referee first measure Alice's message, and then next measure Bob's message based on the measurement result on the Alice's message. So our idea is to consider reduction to the hybrid model, okay, by making the first reference measurement. Alice make the first reference measurement. Okay. So okay, and then let's make Alice send the first measurement result to the referee. However, this idea does not directly work because measurement result can be, generally speaking, measurement result can be much larger than the original quantum message size. Say n qubit, we can measure n qubit state by adding larger ancilla, and the measurement outcome can be 2 to the n classical bits. So to overcome the issue, we introduce some we use some techniques. So the first technique is property shown by Osmanik et al. In 2017. So any POV measurement can be in fact simulated with a small ancilla qubit and some randomized measurement. So we can compress the outcome of measurement result. However, this randomized measurement requires sample from probabilistic distribution over some large alphabet size. So so we can reduce from quantum one-way LCC model to hybrid SMP model with some shared randomness over Alice and referee. And another technique we use is theorem shown by Newman in 1991. So in communication complex setting, it is known that, in fact, a shared randomness can be reduced to small randomness by allowing some small error probability. So exploiting this technique, we show that suppose that there exists quantum one-way LCC SMP protocol for the function f, where Alice's message size is A and Bob's message is B. Then we can construct a hybrid SMP model of Alice's message is 2A plus order log n bits and Bob's message of B qubit. And by combining this reduction and the known lower bound of the hybrid model for the equality function, we can show that the equality is hard for quantum one-way logician. And for the two-way logician model, we exploit some property related shadow tomography. And sorry, due to the time constraint, let me skip some detail. So, but for proving some lower bound against some restrict type of two-way logician measurement, we exploit Aronson's idea related shadow tomography. And finally, we show that some separation between quantum one-way and two-way logician model by considering some variant of the hidden matching problem, first introduced by Bayozev et al. In 2004. Okay, so this is the summary of my talk. So we introduce quantum LCC SMP model, where Alice and Bob can send quantum message, but the referee is prohibited to do entangled measurement. And the equality problem is hard against some restrict type of LCC measurement, and some separation between one-way and two-way LCC model by considering other problem. So, and finally, we so while we could not prove them, we conjecture that the equality problem is hard against general LCC measurement, and the LCC measurement is a special type of separable measurement. So, more strongly, we conjecture that the equality problem is hard against any separable measurement. And yeah, so the problem is equivalently we can consider this game. So referee knows set of states from Alice and Bob with 2 to the n indices, and the referee's task is distinguish. So given one copy of states, the task for the referee is distinguish the indices are the same or not with LCC measurement. And we want to bound the lower, we want to get some lower bound of the dimension. So I think this is a fundamental question. So I hope some progress will be obtained. That's for my talk. Thank you for your attention.
Thank you for nice talk. So I have several comments. So for example, in the area of QKD, there is a method for the error verification. Do you know this one? Error verification.
No.
This is a very common method for in quantum key distribution. So usually at that time, usually we make error correction first, but we don't know the exact error rate. So in that case, we need to check this has no error or not. So in order to make this, people exchange the hash value of that one. So in that case, the amount of communication is not so many. Of course, in that case, it is enough to consider a referee. So because in that case, in the case of the error verification, two-party exchange the hash value of the each obtained random variable, but of course, it is enough to check they are correct, same or not by referee. So then that method can use in your setting. So, but I cannot remember how much
how much communication rate is required? Of course, in order to make that kind of hash value, so we need to two party need to share randomness, common random.
Okay, so, but okay, so yeah, thank you for your comment, and I will check some related papers on error verification in QKD.
Yes, so,
But in SMP model for the equality problem, usually we don't consider shared randomness between Alice and Bob.
I see, of course, but now you are considering shared randomness, no? I'm slightly confused. No shared randomness.
No shared randomness between Alice and Bob.
I see.
Because if they shared randomness, then the equality problem becomes very easy.
So yeah, of course, now I mentioned that, so. But still this requires some log n or some quantity, no?
So
Shared randomness.
yeah, so in this strategy, we consider shared randomness between Alice and referee, not Alice and Bob.
Alice and referee?
Yeah. So this is yeah, the setting is different. Yeah, so to recover original outcome of POV measurement, referee need to know which unitary Alice applied. So this shared randomness is required to recover the original POV measurement from randomized projective measurement.
Shared randomness between Alice and referee.
Yeah, so this is just required to in our proof strategy. So in the
but looks like quite strange. Could you back to the formulation? So this is only solution, but
yes.
How did you formulate the problem? So
Problem is Alice and Bob. Yeah, so referee gets some rho x and sigma y.
No. Firstly, you consider classical case. Classical case.
Classical case. Classical case is yes. So referee want to know x is equal to y or not by receiving messages from Alice and Bob. And yeah, so this problem is, so classically the complexity is known as order of root n if shared randomness is not allowed between Alice and Bob.
This is the classical case, but you write down quantum.
Yeah, so if for a usual quantum SP model, log n qubit communication protocol is known, which is a quantum fingerprint. And we consider as a setting where referee no entanglement measurement is allowed for the referee, including the swap test.
Yeah, I cannot understand. So I'm confusing which is you write down quantum. So no slide for the quantum classical case.
Yes, but setting is the same. So message from Alice and Bob are classical bits.
And in the so then the required number is ON.
Yeah, for all inputs, X and Y.
I cannot understand.
So in communication complexity, we consider worst case.
So then, ON?
Yeah, for all X and Y, for all inputs.
No. Communication complexity. So how about in the
Okay.
classical case?
Classical case is root n, and the quantum case log n.
Quantum case log n. Oh, Okay, so is there any other comment or? So thank you very much. So we proceed to the next talk. So next talk is Shenzhen side, but this one is still again online. So we had a very bad communication. Sorry. So I didn't clearly mention that we have a conference venue except for the first day. So, but many people misunderstand. We completely closed the Shenzhen venue. So on the first day, attack the typhoon. Typhoon already gone. This is quite difficult. So in some sense, this conference is not so good for in Shenzhen. So sometimes so many trouble. So in Shenzhen side. So
But it's okay.
next speaker is already time. So so okay. So 50. No. 3 minutes. So next speaker is Shu. Next, the Fan Shu, please prepare your slide.
Thank you. I'm online.
So please prepare your slide. So
Yes, I'm prepared. So can I start now or waiting in 2 minutes?
2 minutes.
Okay, thank you.
Okay, time. So please, now we want to start the third talk. The speaker is Zhao Pen Su. The title of this talk is Optimal and Heuristic Strategies for Atom Movement of Compilation in Zone Neutral Atom Quantum Computing. So please start.
Okay, thank you. Good afternoon, everyone. It's my honor to present our recent research on neutral atom-based quantum computing. This is a joint work with my PhD students, Yikang Zhu at USTC. I will introduce our work in the following outline. So first I will give some introduction on background and the neutral atom-based quantum computing setup. In recent years, experiments of quantum computing based on neutral atoms has seen remarkable progress. It has achieved high fidelity and high parallelism quantum gates. Looking from Harvard University developed programmable quantum computing with up to 218 physical qubits, and also demonstrated quantum error correction with 14.8 logical qubits. Recently, we cooperated with Professor Pan from USTC reunite the rearrangement of atom array of 2000 atoms. Compared with other popular physical approach for quantum computing, such as superconducting, neutral atoms based quantum computing had its coherent advantages, which including high scalability, non-coherence time, high fidelity quantum gates, and flexible connectivity of qubits, and also cost effectiveness and experimental simplicity, because this experiment is in room temperature. So this figure is about the atomic energy level diagram. For a single qubit system, the basis state 0 and 1 of a qubit system are represented in this level, these two levels. And the operation on a single qubit is realized by Raman beams. For the controlled gate, two qubit gate, the controlled Z gate can be realized by the pulse strategy shown in subfigure A. If the system is in the state 0, 1 or 1, 0, then the system is dominated by the Hamiltonian H1. If the system the atoms are in the state 1, 1, then the Hamiltonian of the system is H2. And for this setup, if we apply the pulse described in figure A, then we will have these transformations. By appropriately choose the values, the parameters, we can implement the control Z gate on this system. And for the experimental setup, optical tweezers plays a significant role. There are two types of optical tweezer device for tweezers. SLM generate static traps and arbitrary 3D positions, and 2D AOD create mobile tweezers to move atoms between static traps. Regarding the implementation of quantum gates, Raman beams are local and allows local operations on a single qubit. And the Rydberg laser are global, and this is used to execute multi-qubit gates. Okay, and then I will introduce the research problem. The compilation of the general quantum circuit to hardware execution include 3 stages: circuit synthesis, circuit mapping, and scheduling. So the neutral atom-based quantum computing has some new characteristics. It have a native gate state U3 and plus control Z, and it also can native support for CCZ. And the atom movement can replace the need for swap gate in the superconducting platform. And the scheduling problem also involves the timing of atom shunting transfer, and there are also Raman and Rydberg beams. We considered the zoned architecture of neutral atom-based quantum computing. Until now, there are several other approaches, but we choose the zoned architecture. This is proposed by Professor Lukin from Harvard University. 1-qubit gate and 2-qubit gate are executed in the different zones. To be specific, the 1-qubit gate are executed in the storage zone, and when it needs to apply 2-qubit gates, the atoms should be moved to the entanglement zone. So CZ gate, the 2-qubit CZ gate is executed if and only if its atoms are in the same site in the entanglement zone, and then apply the Rydberg laser to apply the CZ gate. So the problem is to calculate to plan the path from the movement, and this whole problem can be concluded as minimize the movement cost. We use the P success as a metric, and it can this equation for the optimization. This equation here, Fg is the fidelity for each gate, and after the optimization of this problem is equivalent to minimizing the number of atom movement runs. So the main constraint in this problem is the constraint of ALD. A 2D ALD generates traps with 2 signals, a vector X and a vector Y. So after input these 2 signals, it can generate a N by M grid of traps, and each position of the cross there is a trap, and it can here should be a atom. So when the single vector X and Y change, then the tweezers move. It takes the atom to move on the plane. And this is an important problem is to avoid atom collision during the movement. So we should keep the relative orders of the signal X and Y. So for this problem, we considered different algorithms. So first, it is a direct algorithm, and it is also optimal algorithm for in respective to the result is use the SMT solver. So we can consider all the constraints of the instruments at the problem and put those constraints into the SMT solver. And finally, we can get optimal path planning. But the problem is that there will be many variables, and the SMT solver to solve this problem need numerous time. It is nearly NP hard, so it is not practical. So second, we developed a more practical algorithm. We call it a hybrid algorithm. So we consider to divide the circuit into different layers. So that the problem for each layer, the problem size is getting small, and then we use the SMT solver to solve the small problems, and finally we can get more practical result. This the outcome will be not optimal, but nearly optimal. But the problem is that the time is not so efficient. So then we developed a heuristic algorithm to get time efficient, and also the result is acceptable. So our overall idea is like this. So we first we simplified the problem in two aspects. First, we consider only use the one AOD in the experiment, and for the sites in the entanglement zone, we only consider the 2x2 grids for the sites. And the second approach for simplification is that after applying a CZ gate in the entanglement zone, the atoms must be immediately returned to the storage zone. So there will be two sequential phases. First, we move the atoms from Z1 to Z2 movement, and then move it back, which is a reverse operation. So now we only need to consider the problem to planning from Z1 to Z2. This can be decomposed into two sub-problems. First, we need to computing the matching, and then computing the movement path. For the matching problem, that is how to map for the CZ gate there, because we need to apply many CZ gate. We need to, and on the entanglement zone, there are many different sites. We need to decide which CZ gate moved to which site. So this is matching problem, and this can be modeled as a bipartite graph matching problem. And this for the matching to solve this problem, we usually to consider the Manhattan distance d as the moving cost, but this will result a problem. It will result the path crossing. Path crossing means the there are probabilities that two atoms may have collisions. So to avoid the crossing path, we use d squared or d power 3 as a cost. This will avoid the atom collision. And then we need to we have decided the matching, and then we consider how to do the movement plan. Our goal is to given the start and end position for all atoms, finish the movement as least round as possible. So we considered a greedy strategy. To be specific, let S be the atom, the state of atoms to be moved in the current ride. If we move atom X and does not conflict with any atoms in S, so then we add X to S. And this is another important point that if it has conflict, so the atom X only conflict with one atoms in the set. So the conflict moves are 1 to 1. So the problem becomes finding a maximum independent state in this conflict graph. And for the initial of the placement, the problem, we have two strategies. The first is to consider the random trials, and the second is the symmetric heuristic algorithm for the initial of the atom positions. But for our current situation, these two strategies do not perform very good. We need to find more clever strategies for initial. Okay, and then I will show our the performance of the strategies, the three algorithms. So we use the Qskit to compile benchmarks into a gate set of U3 and CZ gate. And the dataset, we use hardware efficient ansatz circuit, and then we consider a linear easy model circuit. This is the optimal algorithm by the SMT solver. We can see that the time, it is very time consuming, but the result is really optimal. So it is not so practical. And the hybrid algorithm is a little bit more practical, but it is still need more time. Its time is around for the 20 number of layers or 20 qubits. It nearly need 1,000 seconds for the compilation. So from here we can find that both layers and qubits, the number of qubits, it increase with exponentially. And our heuristic algorithms, it's the time is just less than 10 seconds, but the movement is around 4 times of the optimal result. So it is more practical. So this is our comparison. Okay. Time with qubits. And this is the movement with qubits. Okay, see our result. And For the future work, we will consider the integration with the circuit synthesis techniques, and also we will consider the compilation with quantum error correction codes. And maybe we will also consider some realistic noise models. Okay, so that is my talk. Thank you.
Thank you very much. So could you give me the formulation of your problem? Can you
Pardon?
hear me? Could you show me the formulation of your problem?
Research problem, right?
Yes, formulation.
So in this metric, the key is to be this is fixed, and this is also fixed. So to optimize this metric, it is to optimize the total time t. So total time t is related to the atom movement runs. So this is the key we are considered to optimize to the atom movement runs to have as least as possible.
Looks like quite difficult to understand something like optimum in your talk, optimum. So optimum means that you want to consider some optimization of some quantity under some condition, but you clearly doesn't describe the form that point. So
Okay.
what is the condition? What quantity should be optimized?
Yes, but we put some, let me see. Here are some the constraints, and also we have constraints for the AOD. There are many constraints, but I didn't present here. There are many physical constraints. This is the main one.
But I cannot find what is your task. You mentioned that optimal.
Optimal.
So,
You mean
what the meaning of the optimal? So what do you want to do? What quantity you want to optimize? Minimize or maximize?
Oh, that is to maximize. To maximize the fidelity is the larger the better.
Fidelity.
This is fidelity. The larger the better. And here we had a minus. So we need to this one to be as small as possible. So that is to make total time t as small as possible.
But you didn't explain what is fidelity, what kind of fidelity. You didn't write down the definition of fidelity. This is gate fidelity?
That is gate fidelity.
But quite difficult to understand the formulation.
In practice, for each gate on the circuit, each gate has has fidelity. For the single qubit, its fidelity is around 99.8, and for the two qubit is around now 99.5 in the physical.
Okay. Do you have any question for Nagoya side? Nagoya side, any question?
Yes, we have one. Please wait.
Hello.
Hello. Thank you for the talk. I think that recently, the number of neutral atoms qubits are like thousands, and I wonder if this kind of uh, compression thing can be applied to such huge number of qubits, because your simulation seems up to like n equal 18 or something. So I wonder what is the bottleneck of the scaling of this approach to more like.
Oh, okay. I think the qubits is around in around 200. This thousands is just around about the atom rearrange. It's just atom. It's not
Oh,
qubit.
just trapping.
Yeah.
Oh, standard
And
is
in just a few days ago, a group from Europe has reunited 6,000. Mm. That is just for uh, rearrangement of atom array, not a, qubit operation.
mhm.
Mm.
But then, what is the bottleneck of the scaling of the
Yes,
optimization? Information?
the scalability is very good. It's very good. You think about that the neutral atom based quantum computing just maybe started around less than 10 years. At
Oh,
now,
your algorithm, your simulation,
pardon?
your simulation.
UH
Scaling
means
of your simulation. I mean, the result. Could you show the result, the numerical result?
okay. Yeah. Which one?
So this one is like n. The number of qubit is something like how many?
This is our numerical simulations,
Yeah, yeah, yeah.
not on the real physical experiment.
Yeah. So, to reach the scaling of the physical devices, you need to.
Yes, yes. So this algorithm is not practical because we use SMT solver to find this. This is this result, this movement runs is optimal, but it will cost lots of time. So this is not a practical algorithm. So we have further uh, design.
Okay, so practically you just, give up some optimality and, use more fast but
Yeah,
heuristic.
this is our main result.
Okay.
So it's for even 300 qubits, the
Ah,
compilation is around just seconds.
I see. The heuristic one can go like
Yeah.
300. Okay.
And the movement, the atom movement is just around 4 times of the optimal movement. Around 4 times of optimal movement.
Ah, okay. Thank you. I just missed the numbers here.
Yeah. This is very practical. And during the model, I think we have considered the nearly real. We consider the real physical limitations as our best.
Okay, thank you very much. So now time to the next. Thank you very much. And so now I want to move to the final talk. So could you prepare final talk?
Okay, thanks for invitation. Nice to meet you on site and online. So could you see me screen? If okay, I would like to talk about something related to testing K-block positivity, which is based on the paper joined with Benoit Collins and Omar Fachi, who are in Kyoto University, and Ernest Lyon. And one paper has posted, and another is appear soon, hopefully. And let's begin introduction. So in order to characterize quantum state, we bypass quantum state. We have some setting, the dimension d, and the bypass cube the space. And for any Shoemaker number, no more than k state, we can write it down in this form. And then Shoemaker number k state will be the convex linear combination of Shoemaker number no more than k pure state. So let's deny by this notation. And in particular, for Shoemaker number 1 state is a separable state, which is a convex linear combination of Shoemaker rank 1 pure state, namely the product state. And then we are going to have a final structure of entanglement, and we have the following sequence of inclusion. And then we can look at this from a dual perspective, and is the story of entanglement weakness, which has a definition like that. And in this talk, I will focus on a generalization, which we call the block positivity or K-block positivity. So suppose we have a Hermitian bypass operator, and if it's a K-block positive, then we will have a non-negative expectation value for any Shoemaker number K state. So for the dual, so actually this define the dual cone, and now there is an important thing to know that the K-block positivity and the K positivity are related by the triisomorphism. And now, but we are going to have two NP-hard problem. One is the statistic testing or certifying any state, whether it's a Shoemaker number K state or whether a Hermitian operator is a K-block positive operator. So even for the K equal 1 cases, it's a very non-trivial, and we usually require some to define some hierarchy. For example, the extendability hierarchy and the DPS hierarchy, and this is because the quantum definite theorems, which will provide an approximation by some SDP realization. And here is the two sequences. It finally will meet the separable state, but the bosonic extendability will have a faster convergence. So I will show you the definition. So basically, it's mean that you can extend a state at a state, for example, in level, and then you can implement some permutation, and it's exchangeable, which means that it's invariance under the conjugation of permutation. And the bosonic symmetry means that it's a bi-invariant from both left side and right side. And then you are going to have and then I will show you I will mention a very important theorem called quantum definite theorems, which give you a convergent bounds between the symmetry state the exchangeable or bosonic symmetry, which has a different bounds, but not much more different, and the difference difference between the some convex linear combination of product state. And then as I say, I will focus on the K-block positivity, but for example, there are many related problems, and one of the famous one is the distillability conjecture, which is the five open question in the paper. Actually, is a long-standing question for maybe 20 years. I know very sure, but it's a long-standing problem. So just try to know whether this state or this operator is K-block two block positivity or no. And then we actually back to the definition. We need to when we ask the operator whether it's K-block positive, we just ask the optimization problem, the solution of optimization problem. So the goal of this talk will be, can we reduce the SDP by some, I mean that I will approximately solve this as by hierarchy SDP, and then I will show you how to reduce the SDP by utilizing the symmetry and characterize the SDP complexity. And now, so let's move to the main of this talk. And now we can convert the problem from testing K-block positivity to testing one block positivity, the block positivity by some Q purification. And then it's just to extend this state by some maximal entangled state. And then you are going to have some dual part, which means that the state is in this tensor form. This is the for Alice space, and this is the original operator. And to define the optimization problem, and remember there is a very important thing, because the optimization value will be tested by some non-negative or negative. We don't have a positive value. And then I will based on that, because we just define our problem for the some testing one block positivity. We can require or ask the help from the hierarchy SDP by quantum definition, which means that we can define some hierarchy SDP by extendable state or symmetry state. So, but before going to the further analysis, I will use some trick to convert the U tensor U symmetry to U tensor K symmetry, or unitary conjugate symmetry. We for the purpose to using sure value duality, which means that we can consider some complex conjugate representation by extend the one box to a K-1 box. So in this sense, we just convert the maximum entangled state. And then we have basically we have a two symmetry. One symmetry is the UK symmetry, which is carried by the X and the extension of X. And as in permutation symmetry, because the separability of K of extendable system. And then we are going then we can we can decompose the SDP by some Turing state, which means that we using some grouping averaging. And then we are going to have a many block, and then the optimization problem will ask the minimum block, minimum value from some block. But we are going to then we are facing two questions: how to choose the family of Young diagram, and because you can see that as the increase there are many possibility to have a Young diagram, and a second it will be tremendously problem, tremendously difficult to solve all the block. And then the second question, how to characterize the complexity, and And in particular, the hierarchy collapse because for the cases of K equal D, all the question will turn to the complete positivity problem, which means that we only need to look at the eigenvalue of X. And now, so for this, the rest of this talk will suggest the two questions. So the first, I will argue that the rectangular Young diagram are sufficient for the problem, and then we define some SDP. We just relax the trace equality, and then we can have some construction, and then we can we just know that the optimization problem can be solved on some pure state. And then we consider this state for the SDP we just defined, and this will related to some mu, which is the Young diagram in some sense. I will show you. And then for a purpose, we just look at the Young diagram from a family of rectangular Young diagram with K row. And then I will show you that there is a theorem for that ensure that we can define all SDP from this frequency. And this is the optimized value or minimum value of SDP in level n, and this is the original. I just relax the trace inequality, and then we're going to have some factor multiplier to the optimization problem in definition 4. So it carry the same sense. So we can use this way to testing K-block positivity without any Bayesian. So the Bayesian is maybe happen if you forget this setting, and this ratio can be asymptotically vanish as in increase or the larger in increase. So it will cause some zero. So in this sense, something maybe no maybe negative one, but you will have some 0, 1 or asymptotical 0, 1. So in this sense, we can show the rectangular shape ensure the validity. And then after now that we can define our SDP on a family of rectangular Young diagram, we look at the complexity problem. And then let's back to the general cases. We don't require this Young diagram is a rectangular shape, and actually we can as the previous work, we can show that the block state or the Turing state can be separable in can be decomposed in this way, and this is the sure basis. This is the sure basis from the unitary Turing, unitary K Turing. And this one is should be exchangeable, which means that is a conjugate invariant under permutation. And then we actually have we can see that this one is a kind of intertwining map. And then we in the last step we use the sure value duality again, and this K will be characterized by some irreducible representation of CD. And this mu is come from some little Wood Richardson rule. And then we just focus in the rectangular shape of Young diagram. And this one is for example, in interior point method, we just look at the size of the SDP variable for the unconstrained PSD matrix. And in here, we have now how to generalize the PSD matrix by some chaos operator. So the number of linear independent chaos operator will characterize the SDP complexity. So in this way, we can characterize our SDP complexity by this equation. This is just the sum of dimension of irreducible representation of unitary K unitary D. Sorry. And so now by a Hochland's formula for the semi-standard Young tableau, under the rectangular shape of rectangular Young diagram, we can compute clearly for the complexity of SDP. So there has a two corollary, and the testing the CNK here for the K block positivity actually is have a same big O notation as testing D minus K, which means that they have a finite ratio. And the second is the hierarchy collapse. You can take the K equal D, and you will see that this equation will give you D square. And the last thing I want to mention is that this hierarchy collapse can be looked at from a pictorial representation theoretical viewpoint. And this one is that is me that suppose you want to compute the dimension of UD, you actually can look at the complementary Young diagram. In these cases, this is not the hierarchy collapse cases. So you will going to have some non-trivial complementary Young diagram. And if K equal D, and then you will going to have this one vertical Young diagram as your complementary. So this one is obviously no matter how large your the n is, you will always have this very easy compute one is D minus one. And so this is the end of this talk. Let's get a summary. The main result of this talk is the first we propose a way to formulate a hierarchy SDP approach for testing K block positivity, as well as we show how to do the symmetry reduction based on the UK unitary and the UK symmetry and the permutation symmetry. And the second, we show that the family of rectangular Young diagram is sufficient for testing K block positivity because it doesn't change it doesn't affect it preserves the sign of or negative or zero. And the third, we obtain a formulation to characterize the SDP complexity based on the family of rectangular shape of Young diagram, and this formula can explain the hierarchy collapse from the easily, and we also show you how to look at this from a very illustration way from viewpoint of representation theory. So that's all.
Thank you very much. So I could not understand the formulation of your problem. So K block positivity means that where is that definition?
Okay. Yeah. Sorry. I realized I didn't mention this much. So basically, it's me that you have a bypass operator, and the input will be some pure state with Shoemaker number no more than K. And then if this operator is K block positive, the output will be non-negative. And if this one is no K block positive, the output will be negative.
No. The definition of block positive is SNK or BNK? BPK.
BPK.
SNK, you introduce SNK. So block positive the element of SNK or BPK.
You mean this one?
This one. So what is the definition of block positive?
Block positive is that here.
So the element of the BPK. BPK. Oh, okay, I understand. The next, you move to the CKN. So you consider CKN. I cannot understand why you consider that system. So next.
CK. Okay. maybe I.
Yes, it is. I could not understand why you consider that CKD dimension system.
Because I introduced some Alice's space by tensor product this maximum entangled state, d-dimensional maximum entangled state.
K dimension.
Yeah, k-dimensional. And in this sense, then you can convert the k-block positivity problem to the one block positivity problem, because
Please do not move. So I'm
okay,
confused.
okay,
So,
sorry.
but still I'm very confused because you introduce rho k. Rho k is element of CKD tensor CKD. Rho k.
Yeah.
But xk is element of which operator phi k. Phi k is I k. So I'm very confused because this is xk is the only element of the ck tensor ck. Not there is no d, I think, in the definition of xk.
Yeah, no D for this pure k purification. The D is from the X.
X is BPK. Okay, I understand. So X is the element of the CD tensor CD.
Yes.
And
yes.
XK is the element of CK tensor CK.
Yes.
I see.
Exactly.
I cannot understand why you need to consider let So still I cannot understand. So then fat guys testing K block positivity via K purification. Testing of K block positivity. Fat state is a target. X is you want to check X belong to BPK or not?
Yes.
No, definition.
I say this definition for the optimization problem. Yeah, actually this is a theorem.
No, use.
I say this should be a very non-trivial theorem. Because original problem is that you want to test whether X is a block positive. Then you convert it to a K block positive. You convert it to a optimization problem unrelated to one block positive.
Yes.
So that's the how we read this definition.
Yeah. So maybe I should mention that from this parameterization, and this is you have two label, y and xy and xi and yi, and then you extend this, and I think of this label as LC space, the label of LC space. So you basically have a ij tensor xi, a tensor xi tensor yj. So actually you tensor this one, you separate the I and J label. And then you can find that the block of positivity actually is a sin for the two kind of optimization problem.
Okay, so once you have this optimization problem, next step is to do relaxation to SDP.
Yes.
Use the standard relaxation for separable set.
Yes. Exactly.
Okay.
Standard means that's DPS method. You want to consider generalization of the DPS method.
Yes. Generalization to the K block positivity.
By the way, so there is another method for separability. DPS method is quite famous, as you know.
Yes.
But recently I propose alternative method for the separability.
Yeah. You can share me as the reference, because actually if we have a better way to testing separability, we can have a better way to testing K block.
So then the relative merit between my method and the DPA method is slightly different, depending on some parameter region. So dimension because in the case of separability test, we need to consider some tensor product system. But now you are considering the same dimension, DD. But sometimes we can consider one system is not so large, another one is very big.
Oh,
So in that case, depending on the dimension, sometimes my method is better than their method. Sometimes their method is maybe better.
okay.
So that kind of relative merit depends on the parameter. So I think my method also can be extended to the K block positivity, I think. But
Yeah. I agree
no,
with you.
no.
I think so. I believe we can be
Maybe, but not so easy, I think. So
Yeah, but actually I have a question as you mentioned that you consider some DA and DB which is not equal. So in my understanding that maybe we can extend always is always possible to extend the small dimension to the larger one.
of course, if we increase both sides simultaneously, this is not polynomial, so quite difficult to solve. Almost NP hard, I think. But if you fix the one system and another system increase, in that case, we can solve efficiently.
Okay.
So at least my method works well in that situation.
Okay.
One system fix, another system will increase. So in that case, my method is efficiently solved. That's problem.
Okay, I see. So for example, maybe we have some rank division X. So in this sense, we can try to use your method.
Maybe.
Okay, thank you.
So sorry, Shenzhen side discussing so much. So how about Nagoya side? So do you have any question or comment?
No, yeah.
No comment in Nagoya side?
Sorry, no comment.
Oh, soっか。
So I have another question. How can I understand your main theorem that you relax? You have a chain of inequality.
Which chain quality? You mean this one?
Maybe later you quote it as a theorem.
Okay.
Yeah, this one. How should I understand this one?
So basically you can see, maybe we can look at the asymptotical cases. So the Sn, I use S, but very strange form. And this N will push the bond tighter.
So the original problem is VK, right? We want to estimate this one, and you relax it to W, and later what is S? Sn? Sn is the SDP hierarchy.
Yes. The N level SDP, optimized value of N level SDP.
And this is the one that you actually evaluate.
No, W is evaluate in a special block, rectangular block.
Yes.
And because this is a SDP, let's back to this one. And this one is must be the minimum value of all block.
Yes.
So it should be smaller than this one.
Yes.
There has some step I ski from this talk. So basically you can think of if I look at the W, which is a negative cases. In negative cases, you can think of this is a V. So this one is this inequality whole.
Yes.
And then I mean that the cases that because you will be much bigger or greater as the bigger n increase.
Yes.
And then you will shrink this one finally back to the infinity level. Suppose I can do that. And then you will go to the optimized value of the original one. I mean this one.
Okay.
Yes, this one, this definition. And then it will provide you a bound for the ultimate value of this. And actually, if you consider some minimum one, I mean that the negative one, you will replace this W to the V, to the S, sorry. And because in this sense, I can say that there has something maybe misplacing that this one is suppose this one is larger than 0. You can determine all the SDP, because you can see in this inequality will show you that this value will be 0. So it will be K block positive.
Okay. Yeah.
So there has something missing.
Okay, I guess it's clear. Thank you.
Okay, thank you. Thank you for your comment and question.
Okay, so now I want to close the this workshop. So thank you for attending the both side, Nagoya side and the Shenzhen side. So do you have anything from the Nagoya side?
No, it's okay.
Okay, so thank you very much. So now I want to close the this workshop. So thank you very much.
Thank you for organizer.
Much.
なんか言いました。